Okay, let's have a look at this situation where we have multiple roots, so some factor squared or cubed or whatever the power happens to be, just not power of 1. Turns out this, if you know a polynomial, or sorry, not if you know, but if a polynomial has a root of multiplicity m, then the derivative will have a multiplicity of m minus 1. So what that basically means is if it's a double root, it'll be a solution not only to the function itself, but also the derivative will be 0. It makes sense if you think about it graphically, because if it was a double root, on the x-axis you would draw a turning point. So it's a stationary point. So the first derivative would equal 0. If it was a triple root, you would draw in, like a cubic. So a horizontal point of inflection. So the first derivative would equal 0 and the second derivative would equal 0 as well. So it's like that. I mean, if it was a root to the power of 4, then the first derivative, the second derivative, and the third derivative would be equal to 0 and so on and so on. So let's just prove that. So it has a root at a, multiplicity m. So we know x minus a to the power of m is a factor. All right. Now the thing we have to point out here is m needs to be bigger than 1, of course, because we want it to be a multiple root, and also a is not a root of this other factor qx, because if it was, then it wouldn't be a root of multiplicity m, it'd be m plus something. Let's differentiate using our product rule. So write down the first, diff the second, write down the second, diff the first, and of course when we diff the first we have to use our chain rule, anarchy, bring down the power, lower the power, put the boot in. Okay. Tidying that up, there is a common factor there of x minus a to the power of m minus 1. So thus proving then that we have a root of m minus 1, if of course we can show that in this second factor, a is not a solution of the second factor. So let's have a look at that second factor. Well, we know when we substitute it into x minus a, that part's going to be 0. But what about the mqx? Well, m is just a constant number. Qx. Well, Qx, we said up here that a is not a solution of Qx. So we know it's not going to be a factor of this second one, Rx. So yes, we can write it as x minus a to the power of m minus 1 times Rx, and we know xa is not a root of Rx. So thus we have proven our idea. Okay, let's use the idea. Now they've given us a hint, it's a cubic. So straight away we know there is a real solution. But they've also told us it's got a double root. I can infer from that that all the roots are real. Yep. It's a cubic, so it has 3 roots. All the coefficients are real. So if there are complex roots, they must appear in conjugate pairs. But it has a double root. So one of the roots appears twice. Well, that's 2 of the roots. It only leaves 1. Now, if that double root was the complex root, then the conjugate would appear twice. And I would have 4 roots. Well, that's not possible. So I actually know all the roots of this one will be real. Let's find the derivative rather than trying and guess here, because the beauty of this is with a cubic, differentiate a cubic, you get a quadratic, and a quadratic's a lot easier to solve than a cubic. So we can locate that root quite easily. So we get 2 possibilities, minus third or 3. Now, of course, only one of them is the double root, because remember the key, it has to solve the actual function itself. Now, looking at it, it's going to be x equals 3. Because minus a third would imply 3x plus 1 was a factor. Well, we've got a monic polynomial there. That doesn't mean minus a third might not be. It's just that it's more likely to be the whole number. So I think, well, not possible. Highly unlikely, I suppose is a better way of saying not possible. So, all right, I can factorise x minus 3 squared, and then using a bit of logic, I can work out the other factor. It ends up being x plus 2. Well, there's our solution. Now, if you're solving an equation, yes, it might be a double root, but x equals 3 is just a solution. You don't write it down twice. That's the difference between if they said find the roots. If they said find the roots, then you would write it down twice. But that's not what they're asking. It simply says solve the equation. So x equals 3 is a solution. I like this one because it's kind of cool. You look at the year that it happened, 1991, which is palindromic, But then look at the function they gave us and the coefficients, also palindromic. There's lovely little symmetry to the whole thing. The year was symmetric, the question's symmetric. So let's see what they asked us. So x equals alpha is a root of this quartic. 2 plus b squared can't equal 4a squared. That will become useful later on. They want us to show that alpha can't be 0, it can't be 1, or it can't be -1. So these three things cannot be a solution or a root of this polynomial. Well, I can use the factor theorem. 0 is quite an easy one to check because all I've got to do is sub in 0 and I get 1. So we know alpha can't be 0 because that doesn't work. Now what about 1 or -1? Well, if I sub in 1, I get 2a plus b plus 2. Well, I don't know what a and b is, so I don't know if that's 0 or not. So I'm a bit stuck. So all right, let's do -1. And I get, minus 2ab. I still don't know what a and b is. But now we come back to this piece of information they told me. Right, remember, 2 plus b squared cannot equal 4a squared. Well, if that's true, then 2 plus b cannot equal plus or minus 2a. Well, hang on, look at what we got. 2a plus b plus 2 minus 2a plus b plus 2. We just said b plus 2 can't equal plus or minus 2a, so it'd be impossible to get 0. So plus or minus 2a plus b plus 2 cannot equal 0. So therefore, okay, 1 can't be a solution, -1 can't be a solution as well. Plus we've unlocked the secret to why on earth did they tell us 2 plus b squared? There was the useful piece of information. I suppose when you're solving these sort of questions, you got to wonder why would they tell us that bit of random information? You know, you're probably you have to use it somewhere in the solution. There's a good chance. All right. Now, so we've done part A. Show that the reciprocal of alpha is also a root. Oh, okay. Well, let's sub it in. Sub in 1 on alpha. Righto. Well, I want to try and show this is equal to 0. It proves it's a root. Well, let's write it all as one fraction and have a look at what we get on the top of the fraction. 1 plus a alpha plus b alpha squared plus a alpha cubed plus af. Hang on, that's polynomial alpha. But we know alpha is a root. So polynomial alpha is equal to 0. So polynomial 1 on alpha is also 0. Thus, 1 on alpha is a root. So every time we have a root, its reciprocal is also a root. Deduce that if alpha turns out to be a multiple root, then its multiplicity has to be 2, can't be more than a double root, and the other more interesting bit, 4b must equal 8 plus a squared. Right. If alpha is a double root, then 1 on alpha would also be a double root. Every time you get alpha, you're going to get its reciprocal. That's what we just proved. So if we get alpha twice, we must get its reciprocal twice. So we've got 4 of the roots. Okay. However, our polynomial is a quartic. So it has a maximum of 4 roots. So there can be no more solutions, no more roots. Well, therefore, if it is a multiple root, so I've just assumed it was a double root. So if it is a double root, then yes, I end up with 4 roots. But I can't get anything bigger than that. Because if it was a triple root, then the reciprocal would be a triple root, which would give me 6 roots. But it's a quartic. I can't have more than 4 roots. So the maximum it could be is 2. So if it has a multiple root, our only possibility is a double root, its multiplicity must be 2. So no roots can have multiplicity of greater than 2. Okay, but that doesn't finish our question. We've got to prove that 4b plus equals 8 plus a squared. Well, the derivative, I'll work that out because we know that if it's a double root, it'll be a solution to both its function and its derivative. So there's going to be 3 roots to this cubic. I know one of them is alpha, because alpha is a double root. I know one of the solutions will be its reciprocal, because its reciprocal is a double root. And there must be some third root, which I don't know what it is. I'll just call it beta. Let's play with sum and product of the roots on this cubic. So the sum of the roots will be minus 3/4 a. All right. Sum of the roots 2 at a time. 1 plus alpha beta plus beta on alpha, that'll be a half b. Okay. Well, let's do 3 at a time. 3 at a time is nice because alpha and its reciprocal multiply together to give 1. So I can actually locate beta. Beta is minus a quarter a. All right. Let's tidy it up then. So what are we trying to prove? 4b is 8 plus a squared. Okay, I'm going to substitute that third one, the one where I just found what beta is, I'm going to substitute it into the first one. So I get alpha plus 1 on alpha minus a quarter a, that was what beta was, is minus 3/4 a. So alpha plus 1 on alpha is minus half a. I need to eliminate alpha. There was no alpha in their thing. So let's sub it into the other one. Let's see what we get. I'll sub 3 into 2. Oh, a bit more working out here. So I get 1 minus a quarter a alpha minus a quarter a times 1 on alpha. Well, I've just factorised the minus a quarter a there and I get alpha plus 1 on alpha. Why do that? Well, back over here I've got an expression for alpha plus 1 on alpha. So I can now eliminate the alphas out of my expression. So sub in for alpha plus 1 on alpha, play around with it, and I should, and I do, come up with the expression that they're looking for. It's a bit like parametrics, I guess. You're trying to eliminate the parameter, the thing you don't want there. I don't want the alpha in my expression. Okay. So, Cambridge, 5b. Ooh, and our Patel we have a handful to look at as well.